Welcome, everyone. We're going to get started in just a few seconds here, right at 11:30. All right. Okay, well, welcome, everyone. So glad that you are joining us. I am going to pass it over to our speaker today, David Murray. This is the second part of the webinar that we had on Monday. And before I do that, I just wanted to run through a few housekeeping elements. The first being that the session is recorded, so you will note that, and everyone is going to be put on mute just to ensure that the recording and the audio is clear. Audio and visuals are coming through your computer, which you'll notice you don't need to dial in. And if you're having any issues, you can download the app. There's also some links which I will put in the chat. If you are having any challenges, you can also reach out to me. If you hover towards the bottom of the screen, top and bottom, you'll see there's a few items that you can use to help manage the meeting as we go forward. Most importantly is the chat function. If you have any questions, we are going to take questions at the end of the session. Absolutely would encourage you to put those questions in as David goes through the slides, and then I will read them out at the end. Also, if you have any questions for me directly, you can chat directly to host or presenter. Also a note that all consulting engineers will receive a PDH credit for attending this training session. With that, I will pass it over to you, David.
Fault protection of solidly grounded low voltage systems. This is part 2 of a 2-part series. Today's session deals with multiple sources and the modified differential ground fault scheme. By the end of this webinar, you will have learned about the issues that can occur on multiple source solidly grounded 4-wire electrical distribution systems that have multiple system neutral grounds and 3-pole main and tie circuit breakers. You will learn how LSIG ground fault circuit breakers on multiple source 4-wire systems can experience nuisance tripping on unbalanced loads and failure to trip on ground fault in the absence of a ground fault scheme. You will also learn how the modified differential ground fault scheme overcomes these issues to prevent nuisance tripping and ensure that the proper breakers trip on ground fault. Here is a radial electrical distribution system. It is straightforward to coordinate ground fault protection breakers on a single source radial distribution system. Here I have 2 breakers in series, both with ground fault trip units. The trip curve on the right shows the I2T off ground fault trip curves for the main and feeder breaker. And the protection for ground fault can be pretty easily coordinated between these 2 breakers with the ground fault current pickup settings and the time delay settings. No ground fault scheme per se is required. With multiple sources on 3-phase 4-wire systems, the neutral is common between the sources, as I've shown here in red. In this example, the main and tie breakers are 3-pole and the neutral is unswitched. There is a solid neutral connection between the 2 sources. The neutral terminal of each source is grounded, which you can see right here and here. Hence, there are multiple neutral grounds, which create parallel paths for neutral current and ground fault current to flow. Without a ground fault scheme, these parallel paths can cause a ground fault trip unit to fail to trip on ground fault or to nuisance trip on unbalanced load currents. Rule 10-212 of the 2018 Canadian Electrical Code is titled Grounding Connections for Solidly Grounded Separately Derived AC Systems. By separately derived, it means it's not a service entrance. The supply authority is not providing the transformer. This rule permits the grounded conductors, which is the neutrals, of two or more solidly grounded separately derived systems to be grounded at a single tie point. This slide shows an example of two sources grounded at one point. By grounded at one point, I mean the neutral being grounded at one point. A standby generator and a utility source. The load is connected to the two sources through a 3-pole, 4-wire automatic transfer switch, or ATS. This ATS has a solid neutral. It is unswitched and it joins together the neutrals from both sources. Notice that the generator neutral is grounded at the generator, or the utility source, pardon me, not at the generator, right here. This slide shows an example where single point grounding between a utility source and a generator causes the ground fault protection to malfunction. The generator in this example has a ground fault protection relay, which in reality is an LSIG trip unit on the generator breaker. A couple things I want you to note. Notice here that the automatic transfer switch is switched to the generator. So the generator right now is supplying the load. Number two, the system is grounded at the utility source. So here's the system bonding jumper that joins the bonding system to the neutral right here. It also takes the neutral and grounds it to a grounding electrode through a grounding conductor. Notice that a ground fault has occurred at the load. The ground fault current has to return back to the source, which is the generator. So let's look at the path it has to take. The ground fault current flows through the bonding system to the system bonding jumper at the utility source, where it jumps up to the neutral circuit right here. It now flows, the ground fault current now flows through the neutral back to the generator source to complete the circuit and clear the fault. However, the intention is to clear the fault. However, the ground fault current is now flowing in the neutral conductor through the neutral current sensor of the generator ground fault relay right here. The relay will sense this current to be unbalanced load current, not a ground fault. That's incorrect. Hence, the ground fault relay will fail to trip on ground fault. One solution to this problem is to use a 4-pole automatic transfer switch. That is an ATS with a switched neutral. So here are the 3 phases ABC switched, and here's a switch for the neutral. This allows the generator to have ground fault protection, which is a code requirement for 600 volt systems when the generator breaker can be set to 1000 amps or more. With 4-pole ATSs, the generator neutral must be independently grounded at the generator, as is shown in this drawing excerpted from Appendix B of the 2018 Canadian Electrical Code. There are basically 3 choices, as I see it, for dealing with low voltage, solidly grounded main-time-main systems or multiple source systems. On a 600/347 volt system, if the 347 volt loads are relatively small, consider using a small unity turns ratio delta Y isolation transformer with a 600 volt delta primary and a 347 volt Y secondary, and have that transformer feed the relatively small 347 volt loads. Then the remaining 600 volt system can be 3-wire, and then you have no solid neutral between the sources to worry about, hence no parallel neutral paths to cause nuisance tripping or failure to trip. Obviously, the 3-wire approach cannot be used on 208 120 volt systems because the 120 volt loads require a neutral, hence the system must be 4-wire. If the 3-wire approach is not practical, another solution is to use 4-pole main-time-main circuit breakers. The neutral becomes switched, preventing parallel neutral paths between the 2 sources. If 4-pole circuit breakers are not practical because of space constraints or cost or delivery, Another solution is to use 3-pole main-time-main circuit breakers with a ground fault scheme such as MDGF or modified differential ground fault scheme. Early ground fault schemes used a single point neutral ground at the tie, as is shown on the drawing right here. There's the tie point, the neutral grounded to the grounding electrode, and the bonding system. The problem with single point grounding is that it is easy to defeat. For utility supplied services, the utility normally requires the transformers to be grounded at the transformers, which defeats the single point grounding scheme. For utility supplied service entrances, utilities normally require the source transformers to be grounded at each transformer. Hence, you end up with multiple neutral grounds anyways. Thus, it is not common to provide a single point ground between two transformer sources. And if there were more than two sources, it would become pretty hairy trying to do a single point ground. The single point ground method is not immune to the effects of multiple neutral grounds as shown on this 3-line diagram. In this example, a ground fault current of 1 per unit, which is shown here to the right, on the bus on the right, there's a ground fault current of 1 per unit. It splits into 3 paths. The reason it splits into 3 paths is that the common neutral between both sources and a switchboard is connected. In this case, you can see it's connected to the bonding system at 3 points, at the single point ground tie at the tie point, and at the 2 sources where the utility wants the transformer neutral grounded. So we have a common neutral between the 2 sources connected to the bonding system at 3 points. And that's why the ground fault current of 1 per unit splits into 3 paths as it's returning back to the source that's supplying the ground fault, which in this case, because the source B breaker is open, the tie breaker is closed, and the main 1 breaker is closed, the source is source A. All of the ground fault current going into the bonding system at the point of fault has to return back to source A. But there's 3 paths for it to take, as this example shows. And the problem with that, with the single point ground method, is that the ground fault relay here at the single point tie, which is supposed to see the full 1 per unit of ground fault current, it's actually only seeing in this example 0.25 per unit or 25%, possibly preventing the ground fault relay from detecting and tripping the ground fault. This excerpt is from Appendix B of the 2018 Canadian Electrical Code Rule 14-102 for ground fault protection. Multi-fed installations with ties and interconnected neutrals may be grounded at more than 2 locations. In such cases, it will be the responsibility of the system designer to ensure that tripping occurs only on the main breaker associated with the supply affected by the ground fault. So here we have a main tie main arrangement where the 2 main breakers are closed and the tie breaker is open. This drawing illustrates why you cannot simply put LSIG trip units on the 3 main tie main breakers. I have shown a ground fault on bus 2 at the bottom right hand corner of 10,000 amps. And the common neutral of the 2 sources is connected through a system bonding jumper at the source on the right and again at the source on the left. So there are 2 paths for the ground fault current to take through the bonding system to return to the neutral of the source that's supplying the fault current. So since the tie breaker is open and these 2 transformers are not operating in series, or pardon me, in parallel, the fault current has to return by whatever path it takes, it has to return back to source 2 here. And here we have 2 paths. So I just want to describe those 2 paths. In one path, which is to source 2 on the right, 6,000 amps of ground fault current flows through the bonding system to the neutral of source 2 via the system bond jumper. And that it does that to complete the circuit, which is the purpose of the system. One of the purposes of the system bonding jumper is to allow the ground fault to complete the circuit to trip the breaker. In the other path to source 1, 4,000 amp of ground fault current flows through the bonding system, and then through the system bonding jumper to the neutral at source 1. Once this current reaches the source 1 neutral, it then flows through the common neutral over to the source 2 neutral to complete its circuit. So this is the other path. So the 4,000 amps and the 6,000 amps join together so that 10,000 amps returns to the source to complete the ground fault circuit. The undesired effect of these two parallel paths is as follows. The main 2 ground fault trip unit on the right senses only 60% of the ground fault. All of the ground fault current should normally bypass the M2 breaker current sensors. However, because of the parallel neutral path created by the neutral ground at source 1, 40% of the ground fault current actually flows through the neutral sensor of the M2 breaker, which the M2 ground fault trip unit would perceive as unbalanced load current. The result is that main 2 on the right may fail to trip on a ground fault. The other issue is that the main 1 breaker ground fault trip unit on the left sees 40% ground fault current when there is actually no ground fault on bus 1. The 40% of ground fault current flowing through the M1 neutral current sensor does not have an offsetting single phase current flowing through the M1 phase sensors. The sum of the phase and neutral currents will not be 0, but rather 40%, which the relay will perceive, or the trip unit will perceive, to be ground fault current. The result is that you may actually nuisance trip M1, main 1, when there is no ground fault on bus 1. Here we have a main time main arrangement where the main and tie are closed and main 2 is open. So the source 1 transformer on the left is supplying both buses through the closed tie. I've shown a ground fault of 10,000 amps on bus 2 at the bottom right-hand corner. This time I've assumed that the ground fault current will divide up with 60% flowing to source 1, and it'll flow to the source 1 neutral through the bonding system and the system bonding jumper, and 40% will flow of ground fault current through the to the common neutral bus through the system bonding jumper at source, and then will flow back through the common neutral to source 1 to complete the circuit. The problem here is that the M1 ground fault trip unit here only senses 60% of the ground fault. All of the ground fault current, as I mentioned earlier, should normally bypass the M1 breaker current sensors. However, because of the parallel neutral path created by the neutral ground at source 2, 40% of the ground fault current flows through the neutral sensor of the M1 breaker, which the M1 ground fault trip unit senses as unbalanced load. The result is that M1 may fail to trip on a ground fault. Similarly, the tiebreaker sees only 60% of the ground fault current because 40% of the ground fault current is flowing through its neutral sensor through the parallel path created by the multiple neutral grounding points, and then the tiebreaker may fail to trip on ground fault. Here's an example of an unbalanced load. There is no ground fault. The 2 main breakers are closed. Here, closed, closed. The tie is open. Let's assume 100 amps of single phase load current is flowing out of bus 1 from source 1. The 100 amps flows back through the neutral load conductor and reaches the neutral bus in the switchboard. There is a parallel path for the neutral current created by the 2 system bonding jumpers, one at each source. See the 2 system bonding jumpers at each source. This one line diagram, by the way, shows the phase buses as one line. It shows the neutral bus and it shows the ground bus in the double-ended switchboard. I've assumed that 20 amps of the neutral current will divert from switchboard 1 through the parallel path to the system bonding jumper of source 2. That portion of the neutral current will then flow through the internal ground bus of the switchboard over to the system bonding jumper back at source 1, where it will then flow to the neutral of source 1 to complete the circuit. So let's just think about this for a second. We have 100 amps of neutral current. At the end of the day, the 100 amps has to return back to source 1 that's feeding it. But there's two paths. 20 amps is going to go through the common neutral, through the system bonding jumper of source 2 into the ground bus that is in the switchboard between the two sources. And through the ground bus, it will then rejoin and go to source 1. And then it'll rejoin the 80 amps that was flowing through the main 1 circuit breaker. I hope that's clear. So what we have here then is that only 80 amps of the 100 amp neutral current flows through the neutral sensor of M1. The M1 trip unit will sense the missing 20 amps as ground fault current. And I mean, I'm picking 100 amps and 20 amps and 80 amps just for clarity. We would be probably talking 10 times as much current in an actual situation. With M2, brake current M2, there is no unbalanced load on bus 2 in this example. Yet you can see that there is 20 amps of neutral current flowing through the M2 neutral sensor due to the parallel neutral path. The phase and neutral currents flowing through the M2 current sensors will not sum to 0, but to 20 amps, which the trip unit will sense incorrectly as ground fault current. So if the unbalanced load current is high enough to cause the ground fault trip elements to exceed the pickup setting, you could lose both the main 1 and main 2 breaker. Could trip on a falsely sensed ground fault. The modified differential ground fault scheme, or MDGF, is intended for multiple source, solidly grounded, 3-phase, 4-wire systems. The MDGF scheme correctly sums all the circulating currents caused by the multiple neutral paths and grounds. MDGF also achieves selective coordination between the main and tie breakers without having to add a coordination time delay. A switched neutral is not required. MDGF also coordinates with downstream feeder ground fault protection. In this presentation, I demonstrate MDGF on a dual source main tie main system because it's once you understand how it works on that system, you'll understand the concept of MDGF. But I note that MDGF can be configured for systems having more than 2 sources, including generators and transformers. The seminar is based on the Schneider Electric Square D white paper shown here, which is available to anybody. I can email it, or you can download it to this bulletin number from our website. The following components make up the MDGF system. An external set of phase and neutral CTs are added to each main and tiebreaker, shown here. Shown here as 1 0 sequence CT, but it's really 4 CTs, 3 phase CTs, and a neutral CT. The secondary windings of these CTs are connected to the LSIG trip units of each main and tiebreaker. And these, so it's what this is showing here is, for example, T1. This is the ground fault trip element of the LSIG trip unit of breaker T1. That's what that represents. So M2, M1 here is the ground fault G element of the LSIG trip unit of the M1 breaker, and so on. Now, what's interesting here, each of these 3 breakers have internal CTs to monitor for phase over current protection. These external CTs override the internal breaker current sensors to control the ground fault element or G element of the main time main LSIG trip units. So the long time, short time, and instantaneous phase over current protection elements, or LSI elements of the trip unit, continue to receive their current sensor inputs from the 3 internal current sensors in each breaker. Now, when I refer to a ground fault relay, I mean the G element of the LSIG trip unit on each main-time-main circuit breaker. In the wiring schematic, you see the 3 round circles, which I just pointed to. These are the ground fault relays, i.e. the G elements of the LSIG trip units. The external CTs and ground fault relays are configured as shown for a main-time-main application. Notice that the CTs are connected in delta. See? Delta configuration between the 3 sets of CTs. And the ground fault relays are connected in Y inside the delta. Here's a block diagram of the MDGF system for a main-time-main configuration. Please note the following components. The 3-pole circuit breakers with 3 internal current sensors and the LSIG trip unit. The trip unit is the white rectangular box. The external phase and neutral CTs, there's a set of 4 for each breaker. And a ground fault interface module, which converts the CT secondary inputs to be compatible with the G element of the LSIG trip unit. Here are photos, not to scale, of the external CT and ground fault interface module, which is DIN rail mounted. The ground fault interface module provides the interface between the external CTs and the G element of the circuit breaker trip unit, as you can see here in the wiring schematic. So here's the circuit breaker control terminals. Here's the current sensor. In between the two is the ground fault interface module. It receives input from the current sensor and wires out to the circuit breaker to facilitate the ground fault trip. Here's a wiring diagram of the MDGF schematic. Notice that the secondary windings of the external phase and neutral sensors are connected in parallel to produce the sum of the phase and neutral currents at each breaker. In other words, these CT secondary windings are residually connected to detect ground fault current. This typical wiring schematic is hard to read, but there's just one takeaway I want you to have from it. The way MDGF works, it will issue a trip command to trip all sources necessary to de-energize a bus that has a ground fault. For example, if there were a ground fault on bus 2 here, with both main breakers closed and the tie breaker open, then the MDGF scheme will send trip commands to the M2 breaker and the tie breaker, since both breakers can energize bus 2. But obviously the tie breaker is already open, hence a trip command would be redundant. What we do then is short out the G element of a particular breaker with a normally closed auxiliary contact from that breaker. For example, if the tie breaker were open, it's normally closed, tie breaker is open, its normally closed auxiliary contact would be closed. Hence, any trip signal sent by the CTs to the ground fault trip element, the G element, would simply bypass the element through the shorted connection and not issue a trip command to the breaker. So these 3 red circles just show that normally closed auxiliary contacts. MDGF, how it works. To understand how MDGF works on a main-time-main system, I will use this 3-line diagram, which I've taken from the white paper. The G elements of the LSIG trip units, or the ground fault relays, are shown in the center, right here, connected in Y. The circles with letters A, B, and C are just labels to help you identify the CT secondary currents by phase. If you look carefully, you will note that the CT sets are connected in delta. These 3 CT sets are connected in delta. Current can circulate around the delta. While the ground fault relays are connected inside the delta in a Y configuration. In a nutshell, this ground fault scheme captures and redirects the parallel path neutral currents and ground fault currents at the secondary side of the CTs in order to trip the right breakers on ground fault and not nuisance trip on unbalanced load. You can see the primary and secondary polarity marks on the CTs right here. This is a CT by the small black squares. Notice also that each source has two neutral grounds, typical of service entrances, where the neutral is grounded at the transformer as required by the utility, and again at the first switch controlling the system, which is the main switchboard. So here's the switchboard system bonding jumper and upstream transformer system bonding jumper. MDGF permits these multiple grounds. In order to analyze the MDGF circuit, we need to review some fundamentals, starting with CT polarity. On a current transformer, there will be a polarity mark on one side of the CT, one of the secondary terminals, and that polarity mark will be the primary polarity mark. So here's an example, 3 different types of symbols you might see, one of them on the primary side of the CT. One of the secondary terminals, in this case it's this one right here, will also have a polarity mark. Primary current flowing into the polarity mark, primary polarity mark, causes secondary current to flow out of the secondary polarity mark and vice versa. So primary current flowing in to the primary polarity mark will cause secondary current to flow out of the secondary polarity mark and vice versa. We treat the current transformer or current sensor as an ideal current source, which represents infinite impedance when looking back into the secondary windings. If the primary current were 0, the secondary current must also be 0, no matter what voltage is externally supplied to the secondary to force current to flow. That's what infinite impedance looking back into the secondary winding means. Current flows in the secondary only if current flows in the primary. Kirchhoff's current law may be applied to RMS values of AC currents, taking into account phase angles. In our case, we assume the currents are instantaneous values frozen at a specific moment in time. Hence, they can be considered as DC values. We can then disregard the phase angles in the following analysis, just to make it simpler. If you will recall from the Part 1 ground fault protection presentation, 3 sine waves of equal magnitude phase shifted by 120 degrees, as shown here, will sum to 0 at any point in time along the x-axis. Let's look at the point where the blue sine wave, or phase A, is at its peak at x equals 90 degrees. The instantaneous value, we'll call it 1 per unit. The instantaneous values of the phase B and C waveforms at that point is minus 0.5 per unit. These values sum to 0. Hence, if I have waveforms at a moment in time with instantaneous values of +1, minus 0.5, and minus 0.5 per unit, then I know I'm looking at a representation of a balanced 3-phase load. Let's look at CT currents as per unit values as a further simplification. CT primary and secondary currents are considered on a per unit basis. Thus, the ratio of the CT can be ignored in the analysis. If 1 per unit flows into a polarity marked primary winding, then 1 per unit current must flow out of the polarity mark on the secondary side. And here's an example, 2 per unit flowing into the primary polarity mark of this phase ACT, and then there must be 2 per unit secondary current flowing out of the secondary polarity mark of this CT. Now, this slide and the next one are busy. They're hard to read on a small screen. One of the problems of not being there in person to project this on a large screen. So I apologize if it's hard to read. These circuit schematics are also in the white paper if you want to refer to them later. Notice at the top left is a source A transformer, which feeds main breaker A, which in turn supplies bus A at where the red box here is in the bottom. Similarly, at the top right is the source B transformer, which feeds main breaker B, which in turn supplies bus B at the bottom right. In this MDGF application, we have the 2 main breakers closed You can see 52.1 is closed, 52.2 is closed, and the tiebreaker is open. There is unbalanced load on bus A on the left, and there is balanced load on bus B on the right. So I want to show you how MDGF accounts for the unbalanced load and prevents it from being incorrectly perceived as ground fault current. Let's look at the bus B load current at the red box at the bottom right-hand corner right here. There is 1 per unit flowing out of phase B, right here, 1 per unit flowing out, 0.5 per unit flowing into phases A and C. This is a balanced three-phase load. They sum up to 0. Let's look at bus A load in the red box at the bottom left-hand corner. It is an unbalanced load consisting of 2 components, a balanced three-phase load and a single-phase load. 2 per unit current flows out of phase A. 1 per unit is due to the balanced load, and 1 per unit is due to the single-phase load. For the balanced three-phase load, then, there is 1 per unit flowing out of phase A and 0.5 per unit flowing into phases B and C. Superimposed on that balanced three-phase load is a single-phase load. 1 per unit flows out of phase A, and 1 per unit flows back into the neutral. Our analysis will show that none of the main circuit breakers trip on ground fault because there is no ground fault, only unbalanced load current. I showed you earlier that in the absence of a ground fault scheme, by just putting LSIG trip units on the main breakers, an unbalanced load could cause nuisance tripping of the breakers. They could nuisance trip as though a ground fault were present. Please draw your attention again to the 3 Y-connected ground fault relays in the upper center of the drawing. Observe that the CT secondary current flowing into each ground fault relay is 0. 0 into the tie, 0 into the main B breaker, 0 into the main A breaker. And these are 0 into the LSIG trip units. Each of the ground fault relays, which as we know are the G elements of the main circuit breaker trip units, have 0 CT secondary current flowing into them. No nuisance tripping will occur. The CT secondary currents are circulating around the delta, around the delta connected sets of CTs instead of going into the ground fault relays. How do we verify that this is happening? First, we determine the CT secondary currents from the primary currents that we have assumed. Then we sum the CT secondary currents where they come together at various summing points. Remember that each set of 4 CTs at each breaker is residually connected so that the secondary currents are summed. The sum, which is the residual current, is 0 only when the phase A, B, and C and neutral currents sum to 0. I draw your attention to the bottom left-hand red box, which shows the bus A load currents. Look at the 1 per unit neutral load current flowing into bus A. So this is the neutral 1 per unit was flowing out of phase A to the loads and now is back to the neutral conductor to the neutral bus. As you see by tracing it upwards, there's a point at which the neutral current reaches an intersection, which I've circled in red, where 0.25 per unit or 25% of the neutral current is diverted to a parallel neutral path to the right, while 0.75% heads up to return to the source A that's supplying this neutral current. What causes that parallel neutral path? If you look at the dotted line right here between the grounding electrodes, at first it looks like current is flowing through dirt between 2 grounding electrodes that ground the transformers. That is not what's happening because dirt represents too high of an impedance to low voltage currents. This dotted line, in fact, represents the ground bus inside the main switchboard. Okay, back to the neutral current of bus A. Please notice at the intersection, the red circle, that 0.25 per unit of diverted neutral current flows to source B. It reaches the source B switchboard and, if you will, it turns left at the intersection to flow up to the source B neutral terminal, 0.25, there it is. Upon reaching the neutral terminal, The diverted current then flows through the system bonding jumper to the ground bus. This is a system bonding jumper. Then across the ground bus over to the system bonding jumper of source A, where the 0.25 per unit neutral current rejoins its 7.75 per unit brother electrons and flows to the source A neutral as 1 per unit. The multiple neutral grounds create a parallel path in the switchboard. The residually connected CTs on main breaker A are not going to sum to 0 because the neutral current is missing 0.25 per unit. Instead of flowing through the neutral CT of main breaker A, causing the residual current to be 0, it diverted to the parallel path and flowed through the neutral CTs of the tiebreaker and main breaker B. As you might expect, the residual current out of main breaker ACTs is 0.25 per unit, which you can see right here, flowing out of the summing point at the top left of the drawing right here. 0.25 per unit is flowing out of the summing point of these CTs. Here's how we derive the secondary CT currents. Please draw your attention to the left-hand red box, which is bus A. Trace the 1 per unit neutral current as it flows towards the neutral CT on side A. 0.75 per unit flows out of the primary polarity mark of the CT. That means 0.75 per unit current flows into the secondary terminal of secondary polarity mark terminal of the CT. We have just determined the secondary current of the neutral CT of main breaker A. It's that easy. Now let's look at the phase C load current. 0.5 per unit flows up through the phase C CT, flows out of the primary polarity mark, hence 0.5 per unit flows into the secondary polarity mark of the CT. And similarly for phase B. At the bottom left-hand red box, the phase A load current is 2 per unit, and it flows into the primary polarity mark of the phase A CT, right there. Hence, 2 per unit flows out of the secondary polarity mark of the phase ACT. So now we've determined the direction and magnitude of the CT secondary currents. And now we can calculate their sum. And when you add up 2 plus 2 minus 0.5 minus 0.5 minus 0.75, which is what these current directions are, you'll get 0.25 per unit of residual current flows out of the residually connected CTs toward the ground fault relays, right here. A similar analysis of the CT primary and secondary currents through the main breaker BCTs would show that 0.25 per unit residual current flows into the CT secondary summing node. Thus, the residual secondary current out of the main breaker ACTs simply flows into the main breaker BCT secondary circuits. And a similar analysis on the tiebreaker CTs would show that 0.25 per unit residual current flows out of the summing node and in towards the main breaker ACTs. Thus, the 0.25 per unit residual secondary current that would normally cause LSIG trip unit to think there was a ground fault, instead, it's flowing around the delta, and hence none of the current flows into the ground fault trip units. This is how the MDGF scheme corrects for the parallel neutral currents to ensure that no breaker nuisance ground fault trips an unbalanced load. One more brutal slide and we're close to being done. Here, both main breakers are closed and the tie is open. Service A and Service B each have 2 neutral grounds, one at the transformer, the other at the main switchboard. So there's 4 neutral grounding points. There is 1 per unit ground fault current, as you can see on bus A, and that is superimposed on the unbalanced load current of the previous slide. Notice that there is now 3 per unit primary current flowing into the primary polarity mark of the phase ACT because there is And where is that 3 per unit coming from? 1 per unit is from the balanced three-phase load. 1 per unit is from the single-phase load that's on phase A. And 1 per unit is from the ground fault that's on phase A. In this example, all of the neutral current from the unbalanced load flows directly back to source A without splitting into parallel paths, unlike the previous slide. It is the bus A ground fault current that takes parallel paths to return to source A in this example. By whatever paths the bus A ground fault current takes, it must all return to the neutral of source A since the tiebreaker is open. Sources A and B are not in parallel to share the ground fault current. In the bottom left-hand red box, you can see that 1 per unit of ground fault current is flowing from phase A into the bonding system because it's a ground fault. 0.12 per unit, or 12% of that ground fault current, flows to the system bonding jumper of source A. You can see right here at the top. It's hard to read, but that's 0.12 per unit of this ground fault current is flowing into the system bonding jumper at source A. The other 88%, or 0.88 per unit, diverts into the system bonding jumper at the source B transformer right here. So the ground fault current flowing here into the bonding system splits into two paths, the system bonding jumpers at each transformer. Now, looking at the top right-hand red box, notice that 0.8 per unit, 0.88 per unit of ground fault current, which is now flowing into neutral conductor of source B, having arrived there through the system bonding jumper. This 0.88 per unit of ground fault current diverges into two more paths. 0.5 per unit continues flowing along the common neutral. 0.38 per unit diverges to the ground bus of the switchboard through the system bonding jumper at the main breaker of switchboard B. You can see this right here in the red box. The 0.38 per unit current flows through the switchboard ground bus to the system bonding jumper over at the left of switchboard A, right here, 0.38. So the 0.38 per unit flows into the system bonding jumper to return to the source A neutral. Now let's go to the upper right-hand red box. Look at that 0.5 per unit of ground fault current that is flowing into neutral of switchboard B. This 0.5 per unit ground fault current flows through the neutral CT of the main breaker B to the tie bus neutral, where you can see it flows through the tie bus neutral on its way back to source A. It flows through the tiebreaker neutral CT. The 0.5 per unit ground fault current flowing through the common neutral then turns right, if you will, when it reaches the neutral bus of switchboard A. This 0.5 per unit of ground fault current joins with the 1 per unit of unbalanced load current such that 1.5 per unit of neutral current flows through the neutral CT of main breaker A. In the upper left-hand red corner box, the ground fault currents combine at the source A neutral from three paths: 0.5 per unit from the neutral of the switchboard, 0.38 per unit from the ground bus, and 0.12 per unit from the source A bonding jumper. A total of 1 per unit ground fault current, which joins with the 1 per unit of neutral current in the unbalanced load. That's why you see 2 per unit current flowing into the source neutral at the upper right-hand corner box. So where does this lead us? Since we have a ground fault on bus A, we expect the MDGF system to isolate and de-energize bus A from all sources of power by tripping main breaker A and the tiebreaker. We expect it to leave bus B energized. Please look at the three Y-connected ground fault relays in the upper center of the drawing. Notice that 1 per unit of residual current from the delta connected CT sets, representing the full amount of ground fault current, 1 per unit, flows into the ground fault relays of the tiebreaker and main breaker A. 1 per unit into the tiebreaker, 1 per unit into breaker A. Notice that 0 per unit of secondary current flows into the ground fault relay of main breaker B. which remains closed. The MDGF system has done its job again of capturing and redirecting the ground fault current from its multiple parallel paths so as to trip the right breakers on ground fault. If you perform the analysis we did on the previous slide, where you determine the primary currents flowing into the 12 CTs, then determine the secondary currents and total them up at the summing points where the residual currents are created, you will find that CT secondary currents flow properly into the Y-connected ground fault relays so as to trip only the breakers that need tripping without nuisance tripping any other breaker. I'm not going to burden you with any more analysis because this presentation is almost done. On this slide, I just want to point out the following. Main breaker A is closed. Main breaker B is closed. Sorry, the tie breaker is closed. The main A and tie are closed. Main breaker B is open. There is 1 per unit ground fault on bus B, which you can see in the bottom right-hand corner. We want faulted bus B isolated and de-energized from all sources of power. Hence, we want the MDGF system to trip both the tie breaker and main breaker B. We want bus A to remain energized. Notice at the Y-connected ground fault relays that main breaker B and the tie breaker both receive the full 1 per unit residual current from the delta-connected CT sets in order to trip. Breaker A remains closed with no residual current flowing through its ground fault relay. This slide is just to show you that MDGF works when all 3 main tie main breakers are closed and the source is operating in parallel. One other point I need to make, MDGF requires no coordination time delay between the main and tie breakers to be selective. Since we are using the ground fault element of each breaker's trip unit, just providing a different set of CT inputs, the ground fault setting dials of the pickup and time delay on the LSI trip unit apply. Thus, you can easily coordinate the ground fault settings of the main and tie breakers with the downstream feeder ground fault breakers. To conclude, MDGF is immune to multiple neutral grounds. It ensures the correct supply breaker trips on ground fault. It de-energizes the faulted bus only. It prevents nuisance tripping due to parallel neutral and ground fault paths created by multiple neutral grounds. It provides selectivity between the main and tie with no coordination time delay required. It does not require switch neutrals, and it coordinates with downstream feeder ground fault protection. There endeth the presentation. Thank you.
Thank you so much. That was fantastic. So much information, David. Do appreciate that. So thank you, everyone. We are now going to move into Q&A. So if you can please type in your questions into the chat. And I know there were a few questions with respect to accessing the certificate, et cetera. I'm going to go through actually a few slides before we read out the questions, so that will hopefully answer some of the questions that have come through. So David, if you wouldn't mind just going to the next slide. Thank you so much. So again, as mentioned, this webinar was recorded and is being recorded, and it will be uploaded within the next 5 to 7 days, and it will be accessible on the same webinar page you registered. But if you did register, you will also get a follow-up email that will provide you a link to this webinar and all of the slides on demand. So that will be available, but we need just a little bit of time. So it's usually within 5 to 7 days. Also, if you have any further information, you can contact us at the information, the email address listed here. And I am going to put everything in the chat, which I've just done, so you can capture the individual links. We also encourage you to register, if you haven't already, to the Consultant Engineer Partner Portal. And I'm going to go through a few slides in a minute on that. That is a great source of information. Also, to see what webinars are coming up, encourage you to go back to the website. Here's a link directly and register. Again, for every webinar that you register, you will absolutely get a follow-up within 5 to 7 days with the recording. I think that was some of the questions. There's also a 1-800 number here. And then with respect to the training credit, yes, you will receive your credit information following the webinars. I did just reach out to the team, and what we are doing is we're compiling all of them. So it won't be after each individual webinar. At the end of all of the webinars, they will compile them and they will send them out to you. We're also looking at an automated system potentially through the partner portal. So a great idea to register for that. But those will be sent out at the end of the series. We will be compiling them and sending them out to everyone. I hope that answers the question. If you quickly can go through the remaining slides, and again, I encourage you to put any questions into the chat. I'll read them out following these few slides just to talk a little bit about this partner portal where we've consolidated and organized all relevant consultant information on this portal. Next slide just highlights what you can access. It's a library of webinars, spec templates you'll see, white papers, and other technical resources. On the next slide, yes, thank you. All upcoming specifier related and PDH eligible webinars will be on the homepage. So it's a great way to access and stay up to date with information. Also on the next slide, we do have Layout Fast that's also available on the portal. And I know that there's a webinar coming up on Monday, June 1st. So be sure to register for that, allowing you to import our accurately sized Schneider product models with the electrical data already pre-configured into Revit. So this is available through the portal as well. Next slide, you can also use the portal. It has design tools such as selective coordination as well as an arc flash analysis tool. And it's very easy to register. If you just click to the next slide, we're showing you you just log in at the top right-hand corner of the Schneider Electric Canada homepage. And on the next slide, we've just showed you very clearly, you just need an email and a password. And finally, on the last slide, if you could just take a few minutes to provide us some feedback at the link here. Again, I've put it into the chat. We do appreciate that and allows us to ensure that we are getting you the information you need and that is relevant and valuable to you. Okay, one of the questions I did get, David, was with respect to the white paper you were referencing and how they access that.
If you or get the number, the document number, you can just type that into the our website search, and it'll take you right to the white paper. Or you can contact me, and I'll happily email it to you. But it's readily available on our from the Schneider website.
Perfect. One other question just came in, and again, I encourage you to send them through. We have 3 more minutes so we can cover 1 or 2 questions. Will high resistance ground configurations work with the MDGF scheme?
The beauty of high resistance grounding is that it is a 3-wire system only. The neutral is grounded through a neutral grounding resistor at the source, transformer or generator. Hence, you don't distribute the neutral throughout the load, and that eliminates the parallel neutral paths because you don't even have a neutral. So you don't need MDGF whenever you have a high resistance grounded system, or for that matter, a 3-wire solidly grounded system. It's the common neutral path between on 4-wire systems that drives the need for an MDGF ground fault scheme.
Perfect.
Good question. Thank you.
Okay, no problem. So I don't have any other questions coming through. David, thank you so much for everything that you covered today. Is there anything you wanted to share before we close off?
Well, I just want to thank everybody for their time. I know this material is somewhat complex. Be happy to discuss any further questions you have offline, and I really appreciate your attendance today. Thank you.
Wonderful. Thank you very much. And thank you everyone for attending. I'm going to close off now. Again, if there's any further questions on the certificate or the recordings, which the recordings will be available within 5 days following your registration and following the webinar, they will be sent to you directly. Just reach out to us. Thank you, everyone. Have a great day.
Thank you.